Okay, thank you very much. Thank you very much for the kind invitation, and it's really a blast for me to be here. Sorry a little bit for the voice. I'll do my best to be understandable, and let's see how this is going. So bear with me. Okay, I use the first 1 or 2 minutes to actually say a little bit about Fortis, which kind of gives the frame of everything else I will be talking about. So Fortis itself is a normal research institute. It's associated with the Technical University of Munich and funded by the Free State of Bavaria. That's outside of the university because it's also kind of this industry-related side to Fortis. We call it theoria cum praxi, like following Leibniz, right? That what we do should have an impact. Otherwise, technology-wise, it's a classical software engineering institute, I would call it. And there are kind of two trends that kind of rolled over us almost. It wasn't kind of a strategy, kind of just happened. The last 7 or 8 years, AI was popping up everywhere and IoT was popping up everywhere. So we call it engineering of software systems which are increasingly autonomous and decentralized, right? And bringing these things together, that's probably also the answer already to, to Martin's question, what is the next big thing? That's the next big thing. Okay, so to be a little bit more precise, what we're doing, so we're kind of building prototypes, right? So trying things out, how the future could look like. And we do that a lot in production, like with 6G, like a wireless factories, these kind of things. Of course, a lot on decentralized energy markets. Also kind of, how can we actually instruct robots more efficiently? These kinds of things, and also classical things like integrated safety and security engineering. Actually, this brain simulator here sounds it's actually more interesting than it sounds. So that's actually part of the Human Brain Project, and there they're using analog computers. Turns out, it's called spiking neural networks, turns out that's exactly the kind of technology we also need to actually field AI in embedded systems, right? Because they're very, very energy efficient. Okay, so that's basically kind of a round trip through current projects at Fortis. Let's have a little look at assured automated driving, right? Because I think most of us are familiar with that. So that's kind of our street legal car at Fortis, like everybody else. It's based on that's probably really difficult to read, sorry for that. But it's an AD driving stack. We integrated that with sensors on the highway to kind of have call it digital twin of everything that's happening around us. Integrate these things, and that's quite a challenge, and sounds easier than it actually is, but this challenge here, kind of the overall challenge of assurance of learning-enabled embedded systems with less cost and effort while satisfying the highest safety and dependability requirements. I think that will follow us the next 20 or 30 years, right? It's so difficult. The only problem is, the systems are already there. Okay, and the same story goes for a lot of all the other examples I gave you here. Let's go deeper into that. So looking in this autonomous driving system, it's an embedded system in the end, right? Classical embedded system, which we develop using the usual V-cycle requirements, logical architecture. Then we go up to the components, autocode them, synthesize them, whatever, and put them together by generating deployments, configuration schedules, and so on, to to a technical architecture. So that's basically kind of the progress that we've been making in embedded systems in probably the last 10 years. And most of these steps can now be automated using actually SMT like technology. There's only one little new thing here in the last 7 or 8 years that's showing up. So new kind of software. The ANN stands here for artificial neural network, which is basically, it's almost like a hardware-like circuit, but it's kind of specified in a different way than we're usually used to, right? It's not LTL. It's not kind of some stream calculus that we just love in formal methods. But the specification is data. That's the whole difference. And we will kind of elaborate on kind of the consequences on this little difference. Actually, the name learning-enabled or learning-enabled components is a little bit of a misnomer currently, because usually the systems are being trained up front and then being put into the system, but they don't continuously learn during operations. At least I haven't seen anything like that in practice. So the only difference actually is that the data is the specification. Okay, that also motivates kind of the outline of this talk. But first talk a bit this artificial neural networks, of what there is to verify about them and what not. And we go on the system level on what we're doing currently. And that has a little bit of look of what the natural next step is, and we call it embodied systems, and also look a little bit about the consequences of this little next step that's happening, which will be big. Okay, put up a lot of these systems challenges. Probably we don't have the time to go through all of them, but we'll do a selection of them at least. It's just to give kind of a flavor of what are kind of the research needs, right, for the future. Okay, learning networks. Actually, I keep calling them learning networks. So I did a master thesis on learning networks in San Diego. And it's still the same things, but call it neural networks if you want. And that actually is the biggest questions on these neural networks. What actually is there that we can verify about a neural network? Right? We have the data. So clearly, we want that the neural network actually approximates kind of this input-output relation that we're given by the data. Otherwise, we don't really have this kind of specifications that we would expect, because this kind of networks are actually used for realizing functions where there is no specification. Right? It's almost impossible to give a specification. Like how would you specify? How would you give a formal specification of a function that should detect gorillas in the rainforest? Right? What are the LTL formulas for that? There are none. So we really have a certain lack of specification for these neural networks. At least I haven't seen many, and usually, when kind of we get approached saying, verify this network, then the usual question is, okay, against which spec? Okay, there is none. There is data. That's all there is. Yeah. How do you specify kind of? Yeah. Okay. I think you got the message. So instead, we kind of look at some kind of more general properties of what we can actually do. Actually, we expect that, if you have kind of this input-output pairs, training data, that the neural network should actually kind of approximate with respect to some given distance the data, right? So you would like to have a recall. That's perfect or almost perfect, depending on the situation. Then, I mean, a big promise of neural networks is generalization, right? You give it some data and magically it generalizes to other things, right? You give it a picture of a cat and then all by magic, you know, it's supposed or it's phrased to also detect kind of all rotations of the cat. Something we would expect. It's not always true. Okay, so we would like to have kind of how well do they generalize? And look at this picture here. So we have kind of a traffic sign. And the question really is, you know, if it's not a perfect traffic sign, if there is, let's say, some dirt on it, or maybe in the US, you know, it could be a bullet hole or whatever. But it's not a perfect sign anymore, right? We would still see this as a traffic sign. But is it also true for our neural network, for our learning network? Usually it's not true. And we have all heard about these terms of adversarial kind of training, which basically means to kind of systematically identify kind of variations of these inputs so we get kind of a different output. So that's a real problem. So we call that kind of resilient. And we actually want to have some bounds. That's actually how we started. We want to have some bounds on how much effort, right, do we actually need to put into changing such a picture so that we get a misclassification. So that means, you know, how much effort does an attacker need to put into his adversarial attack? Or on the nicer kind of issue, our motivation was to kind of get an interface between the sensors and the perception units so that we can actually tolerate some noise. So that was kind of the motivation behind all of this. And so we looked at it, pretty clear, right? A lot of linear operations and so on. And so we actually, it was Qihong, I should mention that, encoded these kinds of problems into a MILP optimization problem, right? We want to have kind of the maximal bound, which is still okay, right? Which we can still tolerate, for which we still can find that the traffic sign is a traffic sign. And okay, I mean, it takes a little bit of effort to actually make these things work and efficient. But it's a usual MILP kind of problem, which we are solving with all kind of the bells and whistles. So we could actually kind of generate this bounds for reasonably sized neural networks. The only problem is these bounds were really, really small, right? So because neural networks do not tend to be all that resilient, right? There's always kind of one pixel you can change somewhere, which kind of screws everything up. Of course, the engineer then tells you it doesn't matter, it will never happen and things like that. But these bounds tend to be really small. And we should also say that the same kind of techniques can not only use for resilient, but also for kind of validating neural networks with respect to some smallish kind of properties. So they are also not correct in any kind of what you would expect from such a neural network. So technically, I think, you know, we solved the problem, modulo some scalability issues. I don't want to oversell it here. But the problem really is that, yeah, the results are not all that promising. So we looked more into kind of going into metrics, right? The usual, going away from verification in the end, right? Coming up with kind of good metrics, you know, that kind of reflect our kind of expectation on the neural network. So we went more into this kind of, that we have a traffic sign, and then we systematically, you know, put some noise or some transformations to it, right? So, for example, you know, you also, I think this is kind of the haze transformation, right? If there is some haze, you know, you still want the traffic sign to be recognized. And you can do that in all kind of directions. And then we did this kind of spider charts, what is kind of the maximum kind of misclassification, or this is kind of the average misclassification. And you kind of get a much better picture of how well such a classifier is actually performing. And I actually think that that's the way to go, right? Have kind of more this of kind of application-specific robustness in variance measures, right? Like put up a little bit of snow, kind of identify classes of affine transformations or homomorphic bendings or whatever, under which you have these kind of invariance. Okay, so we came up with kind of dependability metrics, the RIC metrics for resilience. We've seen that interpretation of what is actually being represented in a neural network. I don't go into that. Correctness, you've seen that. And I go a little bit into the completeness thing. Does the training data actually cover the scenario space? Because that's kind of the crucial thing, right? I've said most of the data is, the neural network is kind of specified by the data. So it's a natural question now, how complete is the specification? And now going back to our examples of self-driving cars, you know, there have been studies that, you know, if you kind of want to have kind of decent kind of accident rates on this planet, you know, you need to do a little bit of effort to identify all kind of these scenarios. And that's a famous study by Rand, Driving to Safety, which basically says, you know, you need kind of hundreds of millions to tens of billions of scenarios, testing scenarios, to be reasonably safe, which of course is out of the question. Right? Of course, there are ways of kind of mitigating that, but that's pretty much kind of the big problem or the big challenge in automated driving, to deal with this huge amount of scenarios that are possible out there. So, what can we do about it? So basically, in the first step, the usual thing, we kind of partitioned this space using attributes. Like, is it sunny? How is the traffic flow? How are drivers behaving, right? And so on. Of course, there are lots of these attributes. And if you cluster the space, giving these attributes, of course, you get an exponential number of possibilities still. So it's an improvement, but still exponential. So what can we do about it? And here comes a little trick for trading complexity with actually precision. So call it a K projection. And so let's say we have this space of, we have like three attributes here, X, Y, and Z, along this X, Y, and Z axis. And kind of with 4 of these red cubes, we can actually project to each kind of 2 hypercube hyperplane fully, right? So we only kind of need 4 of these red cubes instead of 8. And if you calculate that out in general, you get kind of a polynomial number of these cubes. And so you basically can detect, you basically have kind of a coverage criteria that is polynomial. for coverage. And you have kind of a knob which you can turn with the K. So you can either be more efficient or more precise, as usual, right? That's kind of fun technique that we are used in verification. There's also kind of a justification to that. So if you look at accident reports, then these studies, they say or they claim that you usually need to look at kind of the interaction of 5 to 7 of these attributes. So that means that kind of it could actually give a pretty good basis for a safety case for this kind of things, as we only need kind of 5 to 7 projection. Okay, and then the next coolest thing you can do with that, you can do scenario generation and completion. So let's say you have a couple of scenarios which are now labeled by their attributes here. You can actually turn this MILP engine to actually generate kind of a wideish area that if you cover that, will kind of maximize kind of the outcome or the K projection coverage. And if you do that and then use some generative AI, you can actually generate new scenarios. So you basically use this coverage metric to generate kind of a complete set of test cases in a really efficient way. Okay, that's also an interesting slide. So a neural network is a total function. Nothing else, right? It's simple total function, deterministic at that. But it's usually not being specified completely on its input space. So what does it do, or what is it supposed to do on the space that is not really being specified? So in the neural network circles, it's called, it starts hallucinating, but it's a little bit too anthropomorphic for me. I actually call it a bullshit generator. That's what it is. In a very precise technical sense by Harry Frankfurt in his theory on bullshit. In the sense that it doesn't care what is the truth and what is falsity. It just makes things up. It's faking things. Doesn't mean it's lying, right? Because if you're lying, you consciously need to know, or have a concept of a truth. Nothing like that is here. It's just kind of a statistics-driven babbling. And I should add, a very impressive one indeed, right, as we're discovering every day. But that's actually the basic problem, that we have this kind of incomplete specification. So what can we do? The common approach actually is, just scale things up, right? That's kind of also what's being done in the self-driving community, right? They try to imagine every possible kind of scenario that's out there on this planet. Only turns out it's rather resource demanding. There are too many exceptions, black swans, as we call them, which we now need to encode in data. Previously we encoded them in if and else statements, but now they're in data. But there's just too many of them. And very interesting article for a couple of months ago, kind of made the same observation. So we are still waiting for these self-driving cars. They are there in some sense, but not what they intended to be. So in that sense, they're not successful. And we could say that even after 100 billion dollars have been spent, self-driving cars are going nowhere. That's a real possibility. And because of this problem here, and of course, there are kind of theoretical limits. We don't go into that. Okay, so it's kind of like an arms race, right? You just put more and more resources into things and hope that at some point things will be good enough. Could turn out this way. Who knows? Approach 2, let's call it behavioral boundings. And there we just invalidate a neural network for unknown outputs. So we have 2 channels. We have kind of a performant channel, where we use all this cool technology on learning networks. And so that's kind of this channel down here. And that kind of, well, that's from a current DARPA program. Actually, that's from Darren Kofer and his friends. And then you have a safe channel, which looks, are things plausible? And then if there's some doubt on it, switch to a safe channel, which is now being implemented using kind of more traditional kind of methods, like formal methods, right? Of course, as usual with 2 channel systems, we get the switching problems and things like that. And that's actually kind of now the most critical thing there is. And so in our approach, actually, we kind of computed a heat map of neural excitements during the training phase. And let's look it up here. And so now if you get kind of a black swan, then if kind of the generated heat, excitation levels in the neural network at some point is different from what we have ever been observing, then we kind of get the idea that there's something new here. We're not really confident of the result of the neural network. So in such a way, we would then switch to a safe channel. And that's actually, in a lot of these safety critical applications, that's actually how we build in AI-ish systems. This kind of behavioral bounding, simplex architecture, there are hundreds of names. Okay, so we integrated all of that in a tool called Neural Network Development Kit. It has all these metrics, resilience verification, runtime verification using this heat map kind of approach that I just told you. And it also kind of gives a methodology of how to put these things together to actually be able to build up an assurance case. So how things could rationally being put together to actually show that the neural network is safe. We don't do the assurance cases themselves, but there's something called the AMLAS from the University of York, which kind of pretty well fits with our methodology, modulo some wording. And it's available under LGPL. Okay, so that's for the first part of the talk. I should come to the next big game, so I should speed up a little bit. But now let's go on the system level. On the system level, we don't only have a neural network, but we have kind of usual pipelines, right? We have perception, deliberation, execution. So usually in the perception kind of thing, where we kind of build up a context model of the world, we find the neural networks, and here we kind of have classical control, reinforcement learning, whatever, right? But we can think of it as a system, and actually it is a stream transforming control from a stream of raw data to some outputs. So it's a clear mathematical definition of it. So out equals f of in, where f is kind of this pipeline of perception, deliberation followed by execution. Now, if you have a safety envelope, as a subset of the world out there, the invariant to maintain is just f of s, subset of s, as usual. So what is a safety envelope, or how can we get at a safety envelope? Of course, we could learn it kind of from normal behavior. We could use something like suggestions of what is safe driving in that sense, called the responsibility, sensitivity, safety, which kind of formalizes intuitive rules, like the 2-second rule that we all know, right? And puts that into little mathematical equations. And then, okay, that's how we basically get, these are kind of examples of safety envelopes. And then, if we have such a safety envelope, and we're confident that it's a good safety envelope, then we can use standard verification techniques to establish safety invariant. S is a subset of the weakest pre of F with respect to S. Usual thing, right? We have, everything is, yeah, we can use the weakest pre, either deterministically, probabilistically, whatever. Or alternatively, right, let's say, I said, you know, there are no specifications for neural network. We can now, in a system context, we can now generate specifications for the neural network. Just do kind of the weakest pre of these last two stages with respect to the safety envelope. And that will be the post condition of our perception unit, and the precondition is S. So now all of a sudden we can generate a specification. And we can either use that now for verifying the component, the neural network, or we can also use it for training the neural network with these pre or post conditions, either by generating test cases from the pre or post, or even putting kind of pre and post in the learning phase of the neural network itself. So there are techniques for that. Okay, so basically what I'm saying is if we have a safety envelope and we have such a system, then it's usual formal methods, right? We don't even need to care about the data anymore, right? Because we are verifying with respect to the safety envelope. And there should actually be no surprises, you know, if kind of the context model is actually faithfully enough, if the actions are represented, the effects of the actions are being faithfully reflected in the real world, and also if the safety envelope is to reflect something that we could call safety. These are strong assumptions indeed, and I guess you're not the first ones to realize that we always need to operate kind of on these shadows on the wall, right? So that's kind of Plato's cave allegory, right? We don't see the real thing here, we don't see the real ways, but only the picture on the wall. Of course, Plato was apparently not too worried about action because he used to tie up his actors all the time. I don't know why. Okay, but the assumptions are strong indeed if you're talking about the real world. And it's time for a poem. As we know, there are known knowns. There are things we know. We also know there are known unknowns. That is to say, we know there are some things we do not know, but there are also unknown unknowns, the ones we don't know. Beautiful, isn't it? And it perfectly fits kind of the situation that we have here. I guess that was his only poem. Let's look at the safety envelope. Okay, so we have the known safe, right? That was our S, and the complement would be the known unsafe. But there's probably always some grayish area in between, so there is some kind of aleatoric uncertainty. Is it safe or not? And then there's also some epistemic kind of uncertainty, things we just don't know, right? So and we don't know. So we might have kind of an uncertainty about the safety hazards or risk assessment and things like that, which is just incomplete. It always has to be, in some sense, incomplete. So we have kind of two new quadrants here, the unknown safe and the unknown unsafe. And we need to deal them differently, right? So you would actually still expect our little car to somehow perform or operate in this unknown safe environment, right, for performance reasons. Might be a little bit more cautious, but it should still perform here. Whereas in the unknown unsafe world, it clearly things go downhill if you're too adventurous here. So, and if you look at now what are kind of all the sources of uncertainty out there, right? Then all of a sudden all hell breaks loose. It's not only about uncertainty about the safety envelope, it's also perception uncertainty, sensor imprecision. The inductive learning as such, introduces uncertainty in the generalization. We also had kind of the issue of data correctness, even the labeling, completeness, model correctness, robustness, model uncertainty, right? We don't know, we cannot model all the effects of an action, both aleatorically and epistemically. There's uncertainty on the precision on the context model with respect to the real world, the state dynamics, the dynamics of the operating system. Don't know it exactly. There's also uncertainty to that. Our control might be uncertain, non-deterministic, probabilistic. And then we should also think we're not the only ones on this planet. There are other actors out there, so we need to put their behavior into account too. So all of a sudden, this beautiful world of mathematic modeling kind of seems to break down if you look at that. And how do we deal with that? And basically, kind of a completely different approach to kind of these kind of formal methodist approaches that I told you about. We kind of have a completely new process, and let's call it uncertainty quantification. So identify all relevant sources of uncertainty, quantify and estimate uncertainty, understand how uncertainty accumulates forward and inwards along chains of computations, and reduce overall uncertainty below acceptable levels, and also manage incremental change of uncertainty. So basically, we have kind of the problem of managing uncertainty below certain levels. So I think that's inevitable. It's kind of a revolution in kind of a safety engineering, because we're all losing all this kind of determinism that we all love, because if you have determinism, we can test things. So we kind of put these kind of things together with some partners into a code of practice, and we actually saw some need for that. So this is also Industrial Day. So I mean, we see kind of two kinds of engineers nowadays out there. Let's call them the data engineer and the safety engineer. And the data engineer actually tries to improve its success rates, right? Often kind of in the range 70, 60, 70, 80%, or let's say 88, 89%. And the data engineer is happy, to improve things 2% on a benchmark or something like that, right? That's what she is proud of. Safety engineer is pretty tough, right? The safety engineer seeks justified belief for 99 point, how many nines you like here, of freeness from severe failure. That's a difference. It's a complete difference, right? So So you're a smart audience. I don't do the calculation out here, but you could actually calculate what does it mean, if you put out a pedestrian detection system with 90%, 98% failure rate, which would be really good, out there in the wild, how many accidents you would actually induce with that expectedly, of course, right? So that's what I call the valley of death, right? And that's it's different attitudes of doing things. So the data engineer is the optimist, and the safety engineer is kind of the born pessimist. But we need to make them work together. And that's actually so we actually need kind of a life cycle, actually, a code of practice for ensuring kind of the safety of these learning enabled embedded systems so that these two worlds can actually grow together. And what we did over this last 6 or 7 years is we compiled under the guidance of the DKE, that's the German standardization committee, an international standard which kind of compiled our experience, insight, and results into kind of such a life cycle, which now also integrates these more kind of AI-ish techniques. It's pretty much the same thing as the usual mother norm, IEC 61508, for those who know that. But the new thing is it also kind of includes processes, issues, mitigations, and technologies for actually building AI and ML systems. And as I tried to motivate, uncertainty quantification for managing uncertainty below acceptable level is one of the big things in this new big things in this standard here. Like any other standard, we can only kind of write down what we know. And we must admit, we still don't know enough, what are kind of the good techniques, methods for actually efficiently building a safety case for such a system. We have lots of techniques. There are hundreds, if not thousands, every day, right? New techniques are coming up. But the real problem actually is for the practitioner, which are the methods that actually contribute to my safety case? And on that level, we don't know a lot. Right? We just need much more experience in applying these things. So all these things, all these kind of standards that are going on, they can only be kind of a snapshot. And all of them need to be improved and completed, and so on. Okay, I was a little bit curious, and so I asked some of our colleagues who are consulting a lot also in safety-related embedded systems. So what actually do you do in practice? What do you recommend your customers? I shouldn't have asked. I got back the slide. So that's kind of the current landscape of kind of standards, recommendations, rules, laws, whatever, regulations that you need to obey when you do an industrial implementation of such an AI system. Okay, I was shocked. I don't know how an engineer can do that. Then I said, oh, well, that's kind of only kind of the domain independent kind of slides. But if you put all together, we have about 250 of these on the radar. So it's a messy world out there. And now to go back on the optimistic side, Stephen Hawking, I'm an optimist, and I believe that we can create AI for the good of the world, that it can work in harmony with us. We simply need to be aware of the dangers, identify them, employ the best possible practice in management, and prepare for its consequences well in advance. So in my humble mind, I interpret that as apply good engineering practice. I wouldn't agree with him on the interpretation of simply, but I mean, that's probably the difference between a genius and myself. Embodied actors, the next big thing. So probably you need to invite me again. So I guess I have material for 3 talks. But let's get to kind of what's the next big thing. So currently we are building more or less automated, functionally automated systems, right? Like lane assist, autopilot in a car, in an airplane, flight management system. That's all. But now, also this one is kind of a functionally automated system. It's on its way of actually landing a Boeing 737. But if we kind of envision kind of the next step of it, you could actually see this robot behave as a co-pilot. And actually, starting in 2027, solo flying, at least on some segments of the flight, could already be authorized by EASA. So it might be a good idea to put a robotic co-pilot into the planes. But now, this co-pilot needs to do a lot more things, right? It needs to do radio communication. It needs to read weather report. It needs to integrate all this information to a situational awareness. So pretty much everything a co-pilot does, right? It's kind of a new game. Also, it's getting interesting when things go wrong, right? Then the robot kind of needs an effective explanation of what's going on and also engage in a resolution process with the pilot. And for that, he needs, for example, a model of how the pilot works, right? And in extreme situations, also the robot needs to take over control, needs to deal with inconsistencies. So when things are rough, right, you don't have kind of consistent sensor readings anymore. So, and that's kind of the new kind of systems that are being built, and kind of the potential benefits are clear. And it's not only kind of a co-pilot here, we also have these kind of personal companions, right? How cool would it be to have a companion to do your tax declaration? It's possible, but I'd like this co-pilot here, or to plan trips and things like that. And if you think about it, then basically almost everybody could kind of benefit of such a robot companion. And if it sounds to you a little bit like science fiction, it's not. It's actually old hat. So these kind of software-based companions have been built for 20 years. Pretty successfully, actually, but they're not widespread. I don't know why, but technically we can build these things. I go over these slides. So basically, this kind of new systems that we kind of see popping up already, they're kind of increasingly autonomic, and they're also self-learning. I think that's their most succinct characteristics. And the new thing is that they're actually situated and acting in our societal fabric. That means what they do matters, right? It's not sitting on ChatGPT and have fun of what's coming up, right? So think of it, what is happening if ChatGPT is kind of coupled with some action, right? It just doesn't only do the diagnosis, but it also infuses you the medicine, right? So it matters then what the answer is. And so So the embodiment of the actors actually serves the development of flexible, inventive, and optimized actions for goal-oriented and robust behavior in uncertain, complex, and unpredictable real-world environments. And you shouldn't mix it up with embodied intelligence, which is kind of this sci-fi-like artificial intelligence, general artificial intelligence thingy, talking about consciousness and so on. We don't need that. Right? You're only talking about what is needed, right? The cognitive facilities that are needed for realizing these capabilities, but not those that are sufficient. That's kind of the difference between it. So these are two different things. So we are much more practical here than embodied intelligence community. So we are dealing with doing sensible actions in the real world. For everything there is a market value. So we did a study for the German Ministry of Economic Affairs, and I don't know how these guys come up with these numbers, but they always sound impressive. So they see a market value in these things. I think that's and a big market value at that, and also kind of shows what are kind of the domains that are being affected. There's also some danger to it. I guess the original sin of an embodied actor is Tay. Most of you probably heard of it. It's one of these chatbots they put on Twitter, and within a day or two, it wasn't behaving as because it was self-learning, right? And or it learned from other people on Twitter. So I don't know what kind of ground is hanging out there, but really nasty stuff. And so that's kind of the difference between the laboratory and the real world. And so that's the original sin, and we see much more of these original sins in the sense of self-driving cars. So this one is funny, but not every ride ends like that. Okay, so it will be human beings and machines, and once we have, so we'll be optimistic again, and once we have established that, to Harald, possibility to build a two-way bridge between new and confident alliances between them. So trust, right? Trust is actually the central notion here, and it's not a technical kind of definition. Trust is kind of a subjective evaluation of a trust drop and a trustee about something in particular. And my favorite definition is from organizational theory. Trust is the willingness of a party to be vulnerable to the actions of another party on the basis of the expectation that the other will perform a particular action important to the trust, irrespective of the ability to monitor and control that party. So that's pretty much how things work. And of course, there are some kind of ways of promoting trustworthiness. This might not be kind of applicable nowadays, but we can kind of ensure trustworthiness by again, sound engineering practices. That such a system behaves in accordance with societal goals and norms. Of course, we need to know what those are, right? And applicable laws by and large. And the usual thing, barrier, which is more technical again, dependable, safe, and predictable in uncertain and unpredictable contexts, right? That's where we need kind of have a robust behavior. So that's the topic of the talk. I will do 2 slides and then I'm finished. So we go from embedded systems to embodied actors. And seems like a small step, but embedded systems by and large are centralized. Now we have federated systems, right, of dynamic coalitions of actors who are goal-oriented, right, to accomplish something which alone they couldn't do. Completely different thing. Behavior of an embedded system is deterministic because we want to test things, right? The reason for that. Whereas embodied actors are largely unpredictable The context of the embedded systems is well defined, right? The operating context. Here, pretty uncertain. Maintenance are planned updates. Here we have self-learning, right? We need to adapt to the challenges of a world we don't know yet. Requirements in embedded systems is safety, in embedded actors, trustworthiness. All of kind of safety engineering for embedded systems, in the end, relies on a good handover to a responsible human being, hopefully responsible. For an embodied actor, increasingly no. That means traditional safety engineering, right, which we are so happy to have, whenever we are entering an airplane. I'm proud that there is something like DO-178C, is largely not applicable because it requires well-defined operating context, specifications, complete specifications, and ultimate fallback to a human operator. So that's kind of the challenges we're actually facing. How do we deal with that? How do we deal with these new characteristics? And in the paper, I summarized a couple of kind of system level challenges for actually managing or for tackling these kind of problems. Okay. That's all my second talk. Okay, conclusion. We will see increasingly embodied actors as self-sufficient entities of our own economic and societal fabric. And it's quite clear, right? I was not joking, right? The next evolution of conversational agents like ChatGPT and so on, they will also act in the real world. They're not only conversational agents anymore, right? So if you can do the diagnosis, you can also do the treatment. That is where all these value chains are, and which will kind of put our lives upside down in the next couple of years. So we can build these systems right now, but I would say only with unknown risks, because we don't really have kind of the science or the technology to actually ensure robust behavior of things. And so becoming dependent and losing meaningful control over autonomous systems and self-learning systems are real risks. It's probably already there. And so engineering is coming to a climacteric from embedded systems to embodied systems with lots of new challenges. And in this exposition, I actually only concentrated on the technical challenges, but there, of course, there are lots more like societal challenges, legal challenges, and so on. So what is the role of formal methods for trustworthy embodied systems? I think it's necessary, right? It's indispensable, because formal methods is always good when we only have one chance of getting it right. In hardware, right? So if you have a mistake there, and then after tape out, if you want to change, thing doesn't work anymore. Smart contracts, probably even worse. Safety-related controls, the same thing. So embodied actors is also something we only have one chance of getting it right. When it's out there, it's out there. We cannot recall all of them anymore. It's also urgent, and I already said that, because current conversational agents actually turn into embodied actors, whose actions actually matter. And also, the way we are programming currently changes dramatically. Right? I don't go into details. We can talk about later. And it's also kind of demanding because there's also kind of increasingly a kind of a self-engineering going on in these embodied actors. So engineering activities that we are kind of happy right nowadays to do with lots of people over lots of years are being done to some extent by embodied actors online and continually in the phase of adaptation. So it's a completely new game. And it's also for real. And I think that's an opportunity that an embodied actor deals with lots of real specifications. So, and that's what we like in the formal methods community, specifications. And here I would like to end with actually a question mark to me, to you. Do we go from logical correctness to uncertainty quantification in assuring this kind of systems? Thank you very much.
Yeah, thank you, Harald, for your very nice presentation. So embodied actors are the next big thing. And do you have questions? Maybe I start with a quick question. So, I mean, my feeling is that in the field of artificial neural networks, we haven't understood so much regarding verification and how to use them in the software engineering process. And you said that you're quite optimistic in general, but doesn't scare you that people are using or going towards embodied actors when there are so many foundational questions are still kind of unsolved?
It doesn't help if I'm scared or not. It's happening.
We have to accept
it's for sure. I mean, we could say, it has a potential of becoming dystopia. But we need to cope with it, and the only thing we can do is do our very best in kind of taming the things. And maybe just one, if I find it, kind of concrete things I think we can do, right? So kind of when we kind of talk to these agents, that apply the methods we are also proud of developing, to actually evaluate how plausible are actually the answers of current conversational agents, right? Which deduction rules are being used? Are they sound? Is it abduction, induction, whatever? Is it bullshit, right? Could be everything. What is the factual support, right? How good is the argument these things are actually making? What reasoning mistakes are being made? How, if at all, can the reasoning be corrected? And probably most importantly, how to actually set up a dialogue to actually get correct answer program, whatever correct means. So I think you all have in the back of your mind, how to apply these kind of techniques to address these kind of problems. I think those are kind of the most immediate one. Of course, it scares me. But we have the methods actually to actually still try to make the world a better place.
Other
something like the red team got the car in the morning and the positive test team got the car in the afternoon. The network then learned the shadow shape in order to predict whether this was a dangerous or a safe. And resilience checking, robustness checking, and so on, and perturbation, none of them will tell you that there was a secret giveaway somewhere. Storing that.
I was referring a little bit to that in the sense, we have lots of methods to do something about a neural network, but how sensible are those techniques actually for actually exactly addressing this and actually the real gaps, right? And we also, that's kind of the first answer. The second answer is, no, that one was already good enough. But yeah, so there are these gaps, and there are also kind of no real kind of analysis, or a kind of eliminative induction or kind of arguments to actually kind of get at a kind of a completeness, a relative completeness of kind of the issues that can arise. I haven't seen these analyses at all. What I see is a flood of techniques, actually also from this community, which addresses something. That's all good, but it doesn't really help to address the real issue, in my opinion. Did I miss anything of your?
Before the next question, maybe the next speakers can come up to the front and connect their computers.
When actually at the beginning of your talk, when you talked about, learning from examples and then generalization, and the problems therein, this reminded me of a problem that we actually now have in software engineering with real neural networks, biological ones, namely test-driven and agile development, where people just start from examples and try to build systems, and more we see disastrous outcomes of these projects because they never got the big picture. So I think there's something in that approach, there's something broken if you just focus on it. And I wonder if we are hitting in a much more general and in some sense more dangerous world looking at artificial neural networks. Any comments on that? Because there is a fundamental flaw in the way the problem is approached or a solution is envisioned.
Clearly, I mean, look at the numbers. There is kind of a recent report of, how much of engineering we actually spend in software systems, right? I forgot the title. It's something called unsafe software deal cost us, something like that. I need to look it up. But I mean, the numbers are staggering, right? I think it's about $2 trillion in the US alone for debugging. And most of these errors are being introduced by fixing other errors. Of course, the system is broken. We're spending $6 trillion on cybersecurity of things, that we as a community have solved 40 years ago, probably. Our predecessors already. Of course, the system is broken, and formal message to the rescue.
Yeah, maybe we should. Sorry, yeah.
You spoke about uncertainty.
And
you spoke about uncertainty and the need of managing uncertainty. You think that measuring uncertainty as just as a range of stochastic variables is a good way, or do we need a more fundamental theory to support the kind of uncertainty given by AI-based systems?
Oh, that's a tough one.
I know.
I mean, uncertainty quantification is kind of establishing itself right now as a field, right? It's not a field yet. It has very heterogeneous kind of technologies. And I think it's already happening, what you're suggesting, right? That we're kind of combining different kind of methods of dealing with uncertainty, like probability, like non-determinism, right? That we do in our abstract interpretation, statistical moments, information theory, right? All these kind of things we need to deal with. I think they're good technical kind of individual approaches, but how to combine them, we don't really know. Plus, a lot of the work on uncertainty quantification and risk analysis usually is based on smallish kind of problems, 20 variables, 30 variables. I actually think, we need a kind of, let's call it an engineering calculus, for composing uncertainty and maybe even different kinds of uncertainties, to actually scale these techniques up to the level of what you actually need. I haven't seen a lot in that direction, but yeah. So the question was, do we need? I mean, we have a good foundation. We have all kinds of, the basic technologies are, I would say, there, right? From risk analysis, from probability theory, from formal methods, but we need to scale it up in kind of an engineering calculus. So that would be my answer to your question, and I would be happy to discuss on that one all week long.
Yeah, I think we have to move on with the program. Let's thank Harald again for his presentation. He will be around.